Definition of current and definition of unit of current. Definition. It is defined as the time rate of flow of charge through any cross-section of a conductor. Electric current equivalent to total charge flowing per time taken. I equals to Q by T. Unit. SI unit of electric current is amp. 1 amp equals to 1 coulomb per 1 second. The current through a conductor is said to be 1 amp if 1 coulomb of charge is flowing per second through a section of wire. Direction of current. As a matter of convention, the direction of flow of positive charge gives the direction of current. This is called conventional current. The direction of electrons gives the direction of electronic current.
Ohm's law states that V is proportional to I, where V is the potential difference across the conductor and I is the current flowing through the conductor. Let this be equation 1. To replace the proportionality sign by equality, we introduce a constant and write equation 1 as V is equal to Ri, where R is the constant of proportionality and is called the electrical resistance of the conductor. Let this be equation 2. The SI unit of resistance is ohm. The resistance R of a conductor depends on the composition of the conducting material and the dimensions of the conductor. Resistors are one of the important components in a circuit. Resistors are joined together to form various types of combinations to obtain the required resistance in the following 3 ways. 1. Series combination. 2. Parallel combination. And 3. Mixed combination made up of both series as well as parallel combinations of resistors. We obtain a series combination of resistors by joining one of the 2 endpoints of a resistor to the next resistor. We can make a series combination using 2, 3 and so on up to n resistors. We obtain a parallel combination of resistors by joining one end of all the resistors and similarly joining the other end of all the resistors. A parallel combination can be made using any number of resistors. A mixed combination of resistors is obtained by connecting some resistors in series and some resistors in parallel combination and then connecting the 2 combinations. So far, we have seen how to build various types of combinations of resistors. Next, we will learn about equivalent resistance of any combination of resistors in a circuit. Equivalent resistance is the resistance of a single resistor that can replace the given combination of resistors in the circuit without affecting the total current in the combination and the voltage across the combination. We conclude that when 2 resistors R1 and R2 are connected in series, the combination has an equivalent resistance equal to R1 plus R2. When 3 resistors of resistances R1, R2 and R3 are connected in series, the equivalent resistance for this combination is equal to R1 plus R2 plus R3. We can extend this to a series combination of n number of resistors with resistances R1, R2 and so on up to Rn. The equivalent resistance of this combination is equal to R1 plus R2 and so on up to Rn. we can calculate the equivalent resistance Req of the parallel combination of two resistors. Similarly, when there are n resistors connected in the parallel combination, we can write 1 by Req is equal to 1 by R1 plus 1 by R2 plus and so on up to 1 by Rn. The equivalent EMF of a series combination of n number of cells is the algebraic sum of their individual EMFs. If, in the combination, the current leaves any cell from the negative electrode, the EMF of that cell will bear a negative sign. Rule number 2. The equivalent internal resistance of a series combination of n number of cells is the sum of their internal resistances irrespective of the orientation of the terminals of the cells in the series combination. In the circuit that we used, two positive terminals are joined to each other, and similarly, two negative terminals are joined to each other, and currents I1 and I2 are flowing out of the positive terminals. If the negative terminal of the second cell is connected to the positive terminal of the first, equations 8 and 9 are still valid by replacing E2 with minus E2. Equations 8 and 9 can be extended when n cells of EMF E1 to En with internal resistances R1 to Rn are connected in parallel combination. They can be replaced with a single cell of EMF EEQ and internal resistance Req. We can write 1 by Req is equal to 1 by R1 plus 1 by R2 plus and so on up to 1 by Rn. EEQ by Req is equal to E1 by R1 plus E2 by R2 plus and so on up to En by Rn.
Resistance. Resistance of a material is the property of material, by virtue of which it opposes any flow of current through it. The factors on which resistance of a conductor depends are the length of the conductor, the area of cross-section of conductor, and the nature and temperature of material. Now, let's start with the first factor, that is the length of conductor. So here are two conductors, one is longer than the other. Now, when the electron goes from one point to another inside the conductor, it experiences collisions with their captive electrons, or the stable atoms that are present inside the conductor. As the conductor is not a hollow material, so the electron, when passes through the conductor, has to experience some collisions. Now, the longer is the conductor, or say more is the length of the conductor, more collisions the electron has to suffer. So, when the length of a conductor increases, electrons suffer more collisions, while traveling from one end to another end of the conductor. Hence, the resistance of a conductor increases with the increase in length. Or we can say, the R is directly proportional to L, that is, the resistance is directly proportional to the length of the conductor. The second factor on which the resistance of a conductor depends is the area of cross-section. Again, here are two conductors. The area of cross-section of one is more than the other. So, if we talk about the area of cross-section dependence on the resistance, so when electrons pass through a small area of cross-section, they suffer from more collisions, and hence, the resistance to the flow of electron is more. On the other hand, when electrons pass through a large area of cross-section, they suffer less collisions, and hence the resistance to the flow of electrons is less. So we can say more is the area of cross-section of a conductor, less will be its resistance. And, less will be the area of cross-section of conductor, more will be the resistance. And hence, the resistance is inversely proportional to the area of cross-section. The third factor on which the resistance of a conductor depends is the nature of material. Here are two conductors, having same length and area of cross-section, but the material is different. So, the resistance also depends on the nature of material and the temperature. That temperature dependence we'll discuss later. So, the resistance of a conductor depends on the nature of material of the conductor also. How? Let's see. From the two-factor that is the length and area of cross-section, we have already seen that resistance is directly proportional to the length of the conductor and inversely proportional to the area of cross-section of the conductor. Taking these two as 1 and 2, and combining them, we can write resistance, that is R, is directly proportional to L upon A. If we equate this proportionality, we can write R is equal to rho L upon A, where ρ is the constant of proportionality, that is known as resistivity, or the specific resistance of the material of the conductor. Now let's see what is this resistivity. We have got the expression of resistance as R is equal to rho L upon A. Rearranging it, we can write it as expression of ρ, as ρ is equal to Ra upon L. Now, if the length is taken as 1 unit, and the area is also taken as 1 unit square, or say 1 meter square, so if you substitute the value of length as 1 meter and area as 1 meter square, what value of resistivity we are going to achieve? Well, we will get ρ is equal to R. So, if we calculate there, basically SI unit of resistivity, so what we can write? ρ is equal to ohm meter square upon meter. Substituting all the SI units, so we substituted the SI unit of resistance as ohm, area as meter square, and length as meter. And solving this, we will get the SI unit of resistivity as ohm meter. Now, from all these calculations, resistivity of a material can be defined as resistivity of material is the resistance offered by a conductor having unit length and unit area of cross-section. So this is basically a formal way to define resistivity. Basically, resistivity is the characteristic property of material. It does not depend on the length of conductor and area of cross-section of conductor. Different materials have different resistivities.
Conductivity. Reciprocal of resistivity is called as conductivity. Sigma equals 1. If ρ is resistivity and sigma is conductivity, then sigma is reciprocal of ρ. Its SI unit is Siemens per meter, S/m.